This is Learning Module 8.2, Section 8.2 of the Matter and Interactions textbook. And in this learning module, we discuss more of the details about the absorption and emission of photons by atoms and molecules. So the major point is that in the microscopic world, objects are allowed to occupy only certain energy levels, which is contrasted to the macroscopic world of objects like cars and baseballs and airplanes, which are allowed to have any energy level that you want. So in the quantum mechanical world, that is the microscopic world, which is governed by quantum mechanics, objects, let's consider a hypothetical atom, is allowed to take only certain energy levels. So there is some lowest energy level, E1, which we denote as the ground state. The next energy level that's allowed, E2, is what we call the first excited state. E3 is the second excited state, so on, up until some arbitrary nth energy level, which is the n-1 excited state. Okay, so for an object which has energy levels like this, how does absorption and emission work? So we imagine that we have, say, an atom which is situated with an energy of the ground state, and if this is E2, then if a photon of exactly the right amount of energy, E gamma equal to E2 minus E1, comes along, this atom can absorb that photon and be excited to its second energy level. Then, after we wait a while, the atom will drop back down to its ground state, emitting a photon of exactly the same energy as what was absorbed. So this is the process of absorption, and this is the process of emission. Now, it's important to realize that a photon of a different amount of energy, say E gamma equal to E2 minus E1 plus some small amount more of energy, cannot be absorbed by the ground state. In other words, if that energy E is this energy difference, then I can't absorb just this amount of energy of the photon and let another photon of energy epsilon be released. You have to take either all of the photon or none of the photon. You're not allowed to take pieces of it. Okay, so one consequence of this experimentally is that we can measure what the absorption or emission spectrum of some material is. So to do this, we imagine a sample of material of many atoms, and then we shoot it with some range of light energies. So as we shoot this with different energy photons, gamma 1, gamma 2, etc., down to gamma n, then any photon which matches the energy level of the atoms in this sample may be absorbed. So if on the other side of this sample we put a detector to detect which photons come through on the other side, some of the photons might be absent. Say if gamma 2 has an energy which exactly matches the energy level of one of the atoms in this sample, then it will be absorbed and will not show up on the other side and be detected by the detector. So if several of the photons are absorbed, say gamma 2 and gamma 5, are absorbed by the sample, they won't show up on the detector, so you will have dark patches where no light hits the detector, and this is what's known as the absorption spectrum. Now in practice, the absorption spectrum detects transitions only from the ground state of an atom. The reason for this is that if all the atoms in the sample are already in their ground state, say E1, then although after absorbing a photon and jumping up to E2, you could in principle absorb another photon, which would jump from E2 to E3, that this atom will decay back down to E1 very quickly, so it makes this transition improbable to see, and likely you'll never absorb an E2 to E3 photon or have that transition. So in practice, for absorption, we only get transitions from the ground state. Contrast that with emission, and we suppose instead that we have a sample of atoms which are already all excited. So these might be, all these atoms might be randomly distributed among different energy levels. Now all the transitions between the energy levels are in principle allowed, and now because we have all these atoms in excited states, all of these transitions will be seen by a detector on the other side. So a photon that's released by this transition will be detected here. Photon released by this transition will be detected, and so on. So although, and then you also have this, and finally this transition. So the only transitions that are the same as the absorption are the ones that end at the ground state. So this transition, and one I haven't drawn, this transition would be the same as the absorption spectrum. But in addition to those photons, we also observe transitions between excited states. So for emission, when the photons come back out of the excited states, we see transitions between, say, E3 and E2 will show up on the detector that we would not have found for the absorption spectrum. And then for one definite example, if we consider hydrogen, the energy levels of the hydrogen atom are known exactly. So the formula for the energy of a hydrogen atom in its nth energy level is negative 13.6 eV divided by n squared. So for E1, the energy is negative 13.6 eV. For E2, the energy is negative 13.6 divided by 4 eV, etc., down to E3, which is negative 13.6 over n squared eV. And as a note for units, 1 eV is equal to 1.602 times 10 to the minus 19th, I think. Yes. 1.602 times, approximately 1.602 times 10 to the minus 19th joules. And the way to remember that is that this is the same number that is the fundamental charge, 1.602 times 10 to the minus 19th coulombs of charge. In fact, that's where this number comes from, and that's why it's called an electron volt, is because essentially the number of coulombs is the same as the number of joules. It's a little more complicated than that, but that's basically the point.